My name is Ari Hakimian. I'm an application scientist here at C-Therm. And today our webinar topic is on differential scanning calorimetry, DSC 101 methods and applications. I'll be joined here shortly by my colleague, Dr. Genesis Infante, who will be taking us through the bulk of today's session. But before we hand it off to Genesis, just going to do a quick little introduction to us here at C-Therm. So for those that may be unfamiliar, new to C-Therm, we are really focused on thermal conductivity under the transient class of measurement technique, really with a goal of simplifying thermal conductivity testing for the materials of tomorrow. So our core expertise lies in the thermal conductivity space, and our core instrument platform that we work with is called Trident. Trident, you can see pictured here, is a modular system which brings together 4 different methods for thermal conductivity testing. When we're dealing with a wide variety of material types, testing conditions, this is where there's no one-size-fits-all solution, and it's really good to be able to pivot, of course, into the best option based on the given task at hand. And this quote here really kind of embodies the idea behind Trident. It's one we like to share. When all you have is a hammer, everything looks like a nail. It's a famous quote from Abraham Maslow that really brings together the idea behind Trident. Again, giving you more of that toolbox approach to address your given sample requirements. So for those that are maybe interested in thermal conductivity, learning a little bit more, again, not the focus of today's session, but we do have a full method selection guide available as a free resource download for those that are interested. Definitely feel free to check that out if you're looking to get a little bit more insight on thermal conductivity capabilities from us here at C-Therm. So that being said, just a quick little intro again from my side. At this point, I'm going to go ahead and stop sharing and pass it over to Genesis, who will be taking us through the main content here today. So thank you, Genesis.
Give me a moment here. There we go. Hello, everyone. Okay. Thank you, Arya, for the introduction. So as the title of the webinar session today implied, I will be discussing the DSC technique, or differential scanning calorimetry, mostly covering method and applications. So in general, the agenda for today's session, for the first half, I will be covering some of the more fundamental or basic principles of how the technique works, some basic guidelines on handling on how to do the testing under the DSC technique, maybe better sensitivity, maybe better resolutions, anything that will be relevant when it comes to understanding your thermal properties of your material. And some of these, at the end of that first half, I will also be covering some of the topics, or at least common core testing capabilities that are done under the DSC technique. With the rest of the webinar, I will be showcasing some application notes that features the use of the DSC under different industries, such as polymers and pharmaceuticals, and some quick one about material research in general. And at the end of this session, I will all be covering some of the special capabilities featured under the Rigaku DSC, more specifically the sample observation capabilities. So to start with, what is DSC, right? I've mentioned earlier that the DSC stands for the Differential Scanning Calorimetry. What it means exactly is that it's basically a thermoanalytical technique that measures the difference with the heat flux introduced by the system that required to increase the temperature of the sample and the reference. So quantitatively, at the end of the day, what you're measuring is essentially the physical and chemical changes that are happening within the sample in response to the temperature increase done by the system itself, which is the DSC. This could be endothermic, exothermic, or even changes in heat capacity. So at the core of the method itself, what it is that you're looking at the difference of the heat flow between the reference and the sample. So shown right here is an example of a DSC machine. And the most important part of this machine would be in this thermal chamber shown right here. And if you open that up, typically what you should see is essentially this basic architecture where you'll have a panel or a pan position for a sample and another position, identical position for your reference. And then the whole structure should have, a heating or heat source of sorts, and then you have some sort of a sensing portion of it. So at its most basic level, and I've mentioned this earlier, is that you basically have your sample contained within a crucible, and then another crucible, identical crucible that doesn't have any samples, which is referred to as your reference at this point. And as the system heats up, you're monitoring that change in temperature. And if the sample itself starts absorbing or releasing heat, that difference is subtracted from the reference is subtracted from that event. And essentially what you're seeing is just your thermal events from your samples directly. Some basic concepts that I'll be repeatedly be mentioning throughout this webinar that is, directly involved with the DSC techniques in general is the enthalpy, which is essentially the amount of heat transfer from any thermal event. So that could be endothermic or exothermic release or absorbing of energy through the sample, which is usually normalized with a unit mass. So in this case, it's usually shown as a joules per gram. Another concept would be specific heat capacity, which is the amount of heat that is required to be added or removed for the sample or substance to change its temperature by 1 degree C. And that is typically described with a unit of joules per gram per Kelvin. So shown right here is our typical DSC test graph. What you should do, an XY axis. In this graph, you'd see that at the horizontal x-axis here would be your temperature typically, and on the y-axis is a heat flow described normalized against the mass, so watts per gram. Another typical DSC thermograph would be an indicator whether the up or down is exo or endo. So in this case, up means it's exothermic, and that will be relevant in the next couple slides right here. So one of the most basic thermal behavior you should see in a DSC graph would be either a shift or a baseline shift right here, which clearly or typically an indicator of some sort of a second order phase transition. And classically, it is associated with a glass transition within the material, or even a current point transition within, depending on the material types, typically associated with metals. A exothermic process, so in this case, the graph looks like this, where in this case, it follows that direction right there, where you have an increase or release of energy, which is typically associated with events such as crystallization, curing, or oxidation. And of course, the opposite of that would be endothermic, which is indicative of the heat being absorbed, which is typically associated with, if the material is melting, some sort of solid to solid transition, or denaturing in terms of protein research. So now after covering the basics of the DSC as a concept in general, what I'll be discussing in the next few slides here would be the typical approach when it comes to having a good experimental parameters. And one of the basic would be in terms of like handling your samples in general. So I mentioned that you have a DSC, and that sample or reference would be contained within a specific crucible. And more often than not, the choice in choosing that crucible or sample pan in this case is a big factor that directly affects the quality of your DSC data. So the main factors that you need to consider when it comes to choosing the sample pan would be reactivity, temperature, and pressure. So reactivity in a context where you need to understand that the sample that you'll be handling or testing using the DSC doesn't react directly with the sample pan, right? So typical examples of a pan would be something like aluminum. This is the majority of DSC are done under aluminum pans, or ceramic alumina, and platinum pans typically are used for high temperature applications. And in some cases, less commonly used are glass or stainless steel, depending on your application. So, you need to make sure that when you're handling something, it doesn't react with any of these material. So a metal, for example, you might want to make sure that that metal does not directly react with aluminum or platinum, and you might need to consider alumina or even glass in this case. Another example would be temperature range that you'll be dealing with. Alumina or aluminum tends to be used up to 500 or even 600 degrees Celsius. The aluminum pan or aluminum in general melts at 660. So you need to make sure that you don't go over that temperature range. And if you do, you need to make sure to choose the right aluminum when it comes to that temperature range. Another factor that hasn't been discussed a lot, and it's very relevant to C-Therm in general, is that when choosing a sample pan, you need to make sure, or ideally would be with something that is a high or a good thermal conductivity. And this is associated with the quality of the peak that you'll get. So you'll have a sharper or larger peaks typically for a higher conductivity. So in this case right here, you have a comparison between a ceramic and a metal pan. So alumina versus aluminum. And you can see that the peak, although they are from the same events, are typically sharper for aluminum. And that's because as the thermal event occurs, in this case, a melt, as that occurs, as the energy is being absorbed from the system, that heat transfer from the system into the sample is facilitated in a quicker manner through a material that will conduct heat better. So that's why you have a broader peak right here, where a ceramic tends to have a lower thermal conductivity compared to the aluminum. Another example would be, if you have a crimped or a sealed pan. So when it comes to pressure, for example, do you have evaporation or some sort of a sublimation where a mass loss is involved, right? As a mass loss, when a mass loss happens, there's typically a shift in the baseline, as you can see right here, in a case where the pan is only crimped rather than sealed. So a crimp pan right here, what it does is that you're pushing down the top of the pan, and you're pushing the sample so that the sample has maximum contact with the bottom of the pan itself. And that, again, that is related with the quality of the signal you'll get, because the more contact you have, any heat transfer will not be lost because of that loss in contact, right? So that's what crimping does, is that you push it down as much as possible without compromising the structure of the pan itself. However, crimp does not seal the whole pan. It just pushes it down, and then it still, if there is a mass loss through some sort of gas, evolved gas event, you'll lose some of that mass, and then that's where you want to seal it so that it makes sure that you don't lose any of that mass, and then you basically retain that pristine flat baseline. Okay, so that's pretty much the basics of how to handle DSC testing in general. The other concept that is commonly used and tested with DSC is the measurement of the specific heat capacity of the material. And on top of that, the most common method is typically by doing a sapphire method. And basically what you're doing is that you're calculating the sample's unknown heat capacity, and you're comparing that against the reference, and in this case, the sapphire, which is used as an industry standard because of the reliability and stable heat capacity across a very, very wide temperature range. So the basic baseline steps into that is that you do a measurement, DSC measurement of a blank crucible. So essentially, you're going to just run it without your sample at a specified heating rate and a specified temperature range, and then you'll get a DSC graph. You follow that up with a run using a sapphire reference material. And then finally, you'll do another run with identical testing parameters as the last two runs with the sample. And what you end up getting is this heat flow versus time graph right here, where you have the blank versus the reference, and then your sample compared there. And then based on this graph, what you do is essentially calculate the heat capacity as a function of the heat capacity of the reference, which is the sapphire in this case, and just at the end of the day, you'll get the heat capacity of your material. Another alternative for this would be what we call dynamic DSC or modulated DSC, also often referred to as temperature modulated DSC. And what it is that instead of having a linear heating rate, you also have a sinusoidal type heating rate on top of that. So what you end up doing is almost having this stepwise heating rate, and you get this DSC data where you have a up and down in a sinusoidal signal. And what it does at the end of the day is that it offers really the advantage of obtaining two separate components in this run. One component describes as more of the reversible and the irreversibles. The reversible contains the heat capacity component, and a irreversible would be the more kinetic component of the reaction. And you can do all of that in a single measurement, which is typically harder to do against the conventional sapphire method that I just described. And a more specifically, I guess you can see it here that you can start separating, from the total heat flow that you'll be measuring from that modulated DSC. You can separate the reversible and the non-reversible component from it, and then and get the specific heat capacity from the different type of components. And then on top of that, what you can also get is the things that happen. So let's say crystallization and all of that good stuff. You want to make sure that from the total heat flow, you'll be able to separate those two components in case there is a thermal event occurring during that melt or crystallization or whichever reaction is happening at that specific condition. So kind of like an overview, or I guess a review here, experimental consideration that needs to be, that I've just mentioned earlier, is that, it is very important that you have an effective sample to crucible surface contact, because any heat event, whether that's absorbing or releasing heat, you want to make sure that the device effectively measures that heat transfer as much as possible, and that starts with having a really good setup. You also want to make sure that your crucibles are very inert, compared to your sample, so that like any thermal event happening is not because of your sample reacting with your crucible, but because of the sample itself. And also, temperature and scan rates can be very important, depending on the resolution and whatnot. Also, you can also play around with different atmospheres. So you can run, inert versus oxidative atmosphere to see whether your reaction would have some effects at your thermal events. So moving on with some specific examples right here. I'm going to be highlighting some, DSC is very widely used in a very different space. A lot of them in polymers, it could be in other material type studies. So I'm going to be picking some of these very, very common examples done in literature and in industry in general, related to life sciences or materials research. So starting with polymers. The DSC technique have been extensively used a lot, really, with the recycling in a plastic recycling application. So as you can just imagine, you take different types of plastics, polyethylenes, nylons, polypropylene. So all those common plastics, and then they're all combined together and shredded and whatnot. So you're going to have essentially a mix of different type of plastics in this shredded bin, right? So how do you apply the DSC to be able to identify how much is what into that container? So in that case, you do a DSC run with the mixed polymers, and you see that there are several melting peaks associated with different types of polymers, and then you identify the maximum or the minimum of those peaks at whatever temperature it's occurring. And then you can see that, like, if you do pure DSC testing or melting of a pure polymer, in this case, HDB, polypropylene, nylon 6, and PET, you can see that these are its specific melting temperature. And then you can associate that back to this mixed polymer, identify that, like, oh yeah, I have this much HDP, I have this much polypropylene or nylon or PET in this mix. You can also directly compare the amount by basically calculating the area under this graph. So it's a relative amount that, let's say, 10% of these, 20% of that, 10%, 15, and whatnot, and so on and so forth. So that's one of the most common, or at least one of the most common application of DSC when it comes to polymers. Another interesting concept that also be commonly used for DSC and polymers is the measurement of crystallinity. So in this very much example right here, you have a polyethylene, a bottle, a PET bottle, or water bottle, typically, and you would think that because they're from the same semi-crystalline polymer, in this case PET, they should have similar DSC behavior, right? Turns out that's not the case. If you take the top bit right here, and then you measure that with a DSC, you'll get this kind of like signal where you have some sort of transition, and then some cold crystallization and a melt, right? This is typically indicative of a more amorphous characteristics and a more crystalline characteristics. So it is a mix between amorphous and crystalline. So you're like a more semi-crystalline type for the top. But then if you take the sides or the middle bit of the bottle and do the same measurement, you'll see that it lacks that amorphous character and has a more crystalline characteristics in general. But then you take the bottom, it's actually identical to the top. So you can actually quantify how crystalline each of these PET. And you can do that by doing this equation right here, where you take the enthalpy of the cold crystallization, which is directly associated with the amorphous aspect of the semi-crystalline polymer, and you take this enthalpy of the melt, and you have a reference enthalpy, which we call the H0 right here, which is directly associated with a fully or mostly crystalline aspect of the polyethylene or form, sorry, which again you assume is 0% amorphous characteristics, and then you put it in this equation where the difference between the two divided by that enthalpy times 100, and that's your percentage of crystallinity. And another, again, directly related to that semi-crystalline subject for the PET, you can also explore how crystallinity is directly affected by thermal treatment of the plastic. And in this case, again, we're coming back to that PET, where the top curve right here is essentially you have a PET melted all the way on the top, and then you cool it down to very fast, so 80 degrees C per minute. And what you end up getting is this increased amorphous characteristic for the PET. When you do the same thing, you melt it and then you cool it down at a slower rate, about 20 C per minute, so four times slower. What you see is that there's a decrease on the amorphous form of the polymer. And you can see that there's an increased crystallinity by this sharper melt. And then furthermore, if you cool it down a lot slower, by 10 degrees C per minute, you can see that the amorphous characteristics is now practically gone, and what you see is, for the most part, a crystalline form of the PET. And another, very kind of like useful DSC application where you can actually apply both the basics, monitoring the thermal event and also measuring the CP, is for the PCMs or phase change materials. So PCMs are typically used in energy storage, or for the most part, and you'll have the solid form and the liquid form, and depending on the heat being introduced to the system, you'll have a melt, or you'll have basically solidification of that liquid. And in this case, you'll have essentially the quality and the performance of the PCM is highly and directly related to its ability to store heat or release heat, right? So using the DSC, you can monitor what's the CP at the solid state and what's the CP at liquid state, and then you can also even monitor temperature where that occurs. That's one example that where DSC is used in a material research application. And we don't focus a lot on pharmaceuticals in general, but DSC is actually very, very important in pharmaceutical application. It's actually considered as kind of like a golden standard in a way, where it's used to monitor the thermal change during the denaturing of proteins in biopharmaceutical products. It's as I said, the gold standard for essentially measuring the melting temperature during the unfolding of the protein directly, and the TM, or the temperature of melt, or of the protein, is typically associated with the first that 50% of the protein themselves have been denatured, and it's used as a indicator of the quality of the protein that is being engineered in this case. So you monitor the heat capacity change, and you'll have a stable conformer because of the increase in temperature. But then as you further increase of that temperature, you'll see that there is a change in the heat capacity, and then a decrease, or where at the end of the day you'll have 100% unfolded right there. So Typical approach in the pharmaceutical space is to kind of like optimize and try to redesign the protein so that you'll have a better TM value. The higher the TM value typically is associated with a more stable protein, and again, depending on the application that you'd like to see that protein in. And again, and a lot of that is typically done in a micro, what they call the micro DSC scale. So very, very small amount, which means you need to have a hypersensitive DSC to be able to monitor that very, very sensitive thermal event, the unfolding of the protein. So very, very useful for pharmaceuticals, synthetic molecules, and even like isolating any sequential reactions there. So this is just shown with azoxyanisole. And you can see that for one of these Vesta DSC by Rigaku, you'll see that there's a better quality signals compared to, like, let's say the previous model where the baseline is a bit more here. So speaking of which, the final part of this webinar, I'll be showcasing some of that sample observation capabilities that I've been mentioning, specifically with Rigaku's most current model of DSC, the DSC Vesta 2. Here is the specification. So if you're all interested, we can do it from room temperature to 725, which means you can actually do sample observation. So there is a camera installed within the system itself that you enable you to take a peek and actually visualize what's happening with your samples between -70 to 725 degrees Celsius. There are some added cooling units. You can also add some UV lights into it. There are some auto samplers and gas selectors in case you're playing around with, like, induced oxidative experiments, for example. A modulated option for CP measurements is available for this, and there's a wide range of heating rate that you can play around with, from 1 C per hour to 150 C per minute. New to this model is this self-diagnostic capabilities. So what that means is that if there is something wrong or some error in your DSC, the DSC itself is smart enough to be able to tell you that, like, look, this is where the problem is. Please refer to this manual or error number 1, whatever code it is, and you'll be able to kind of like self-diagnose it yourself without and maybe it can be easier to fix down the road. There's an expanded measurement range, which is just basically directly related to a higher sensitivity overall, and which is showcased previously as shown with the micro DSC graph right there. So in this first video, we'll see that the measure of azoxyanisole, essentially. And you can see here that in this camera right here is this yellow powder, and then you can see the temperature at the bottom left right there. First thermal event is a melt, or and then a full-on liquid crystal phase to a liquid phase, and then you can see that as we cool it back down, you can see that it's going to reverse. You can see that it becomes a bit more liquid crystalline again, and as it approaches that temperature point where first crystallization happens, you can see that opaqueness occurs, which is a very exothermic crystallization, and another from yellow to a very, very opaque yellow event. So more often than not, when you're doing a DSC without any of these visualization capability, it's open for interpretation. So you'll see, I see an exothermic event here. Typically, this is crystallization, or endothermic event here, typically melt. But you're never sure exactly what those endothermic peaks would tell you, right? As shown right here, you see you have 2 peaks. It's you'd commonly associate this as like, oh, this must be a solid to liquid a transition, but turns out it's more of a liquid crystalline transition, as shown because of the visual aids added by the sample observation. So, you can see here that, again, this is just a step-by-step of that previous graph. You can see that as I said, change from solid to this liquid crystal 2 form, and then from liquid crystal into liquid. Also, sometimes it's hard to kind of conclude that little tiny peak that you'll see in this case, an example right here, is that whether that is a systematic error, maybe a blip into something happening within the environment itself, or it's actually directly associated with a sample. Having that sample observation capability really kind of like completes the story altogether and gives you an extra assurance that, like, yes, this is what's happening with my material. It's not a complete melt, but more of a transitional melt, or it's not a complete, you know, if there's like a baseline drift, oh, that's decomposition right there, or oxidation as backed up by, color change in the material. And our last example right here is carbamazepine. You can see here that there is that rapid melt and rapid recrystallization. So basically just a polymorphic change within the material itself at about 175 to 180 degrees Celsius. And you can see that it fully goes down to that full melt at about 193, 192 degrees Celsius. So that is the power of the sample observation capability as featured by Rigaku's DSC instrument. And with that, I'll be ending my session right here. Thank you for the attention and the time, and I'd be open the floor for some questions.
Alrighty, folks. Yeah, so just before we get to the Q&A section, we'll just kind of do a little bit of a wrapping up of today's webinar. For those that are interested in maybe looking at some additional content, different resources that are available, definitely check out our website, past webinars, technical libraries, some of the content that was featured today. You can find those written formats there. I'll also make note of a few upcoming webinars that we currently have scheduled. Similar to today's 101 series on DSC, we'll be hosting a TMA 101 on April 23rd and an STA session on May 7th. So of course, today's session featured a lot of the Rigaku product line, the DSC. We also do represent Metrobib for their line of DMA, as well as TAL, which is our contract testing division here. So if you were looking for any type of measurement to be run, maybe you weren't necessarily ready to bring something in-house, we'd be certainly happy to assist with those inquiries. If you'd like to learn a little bit more, maybe have a little bit of a more one-on-one consultation session with us, whether it's on the Rigaku product line or any of the systems that we work with, you can book a free technical consultation, and this would give us some time to go over some of that in further detail. If you liked what you saw and you're looking for some budgetary information, you can also certainly request a quote. These are for free. Just let us know in a reach out to us, and we'd be happy to provide you with that information. Lastly, from folks that might be attending, coming from the academic sector, if you're currently enrolled at an academic institution, we do have an academic support program in place. This is a really nice offering for an overall discount on the Trident thermal system, as well as a few other nice added bonuses in there. So if you are reaching out for budgetary information, you're from a university, definitely feel free to reference that. Lastly, I'll put a little request out there. If you're not already doing so, give us a follow on LinkedIn as well as subscribe to our YouTube channel. This is where we put all of our upcoming content, webinars, application videos, blog posts. So if you're looking to keep up to date with us, this is where it all goes first. All right. But yeah, that brings us to the formal end of today's session. As Genesis mentioned, thank you everyone for your attendance here today. At this point, we'll be closing the live content and transitioning into the Q&A. So thank you very much.